Good afternoon, everyone. How are you guys doing? Did you have a good break? A good weekend? Yes? Are you ready for the exam? No? Okay, we'll talk a little bit about the exam towards the end, but now we just need to close a few things related to shear failure. And if you have some questions, then we'll do that towards the end, okay? Let me tell you something I was forgetting all the time to tell you, and I was meaning, but I was forgetting. But now I wrote it, so I'm not going to forget. And this is the relationship about rock failure and permeability. Why are we interested in learning about rock failure? For a long time, rock failure was mostly limited to understanding drilling and wellbore stability, how you can drill faster, how you can drill wellbores, and so they are stable. But now, in the recent years, we understand a lot more geomechanics, and we understand the advantages of having a rock that has, for example, some permeability that usually when it's not broken, we just call it matrix permeability. And what happens with that rock when we fail it after and we create some fractures? Sometimes we can have shear fractures, like, for example, the ones that you can create with axial compression. So let me zoom in here. You see, all of these are real fractures in a sandstone. And what do you think that's going to cause to permeability? The permeability of the entire rock. It's going to increase it. It's going to increase it, and it's going to make this porous medium, in terms of fluid flow, a lot different to what it was before. This is one option. You can have failure in shear, and that's what we're seeing right now. And what we saw before is that also we can have failure in tension too, which is another type of fracture. But either by shear or by tensile failure, we can alter the permeability of a medium. And then we have now one more component, which is fracture permeability plus matrix permeability. And getting to know how rocks fail in nature, on how they fail when we do hydraulic fracturing or depletion or any other thing, is super important, because it allows us to understand better the variation of permeability, and more importantly, how to manipulate permeability. How, when we have a very tight reservoir with very low permeability, we can increase permeability for example, recovering hydrocarbons a lot faster. It's not the same to have, for example, a particle or a molecule of fluid that needs to go from here to here and to go all the way through the porosity and to small pores, than having a fracture and go from here to there through a highway, which in this case, the highway is going to be a fracture. So please remember that understanding how rocks fail, it allows us to manipulate permeability. And we're going to see how later on with hydraulic fracturing, we combine tensile fractures with shear fractures, and how that impacts into the alteration of the permeability of a reservoir. But everything is closely linked. Okay, so now that I said that, I can move on. All right, so we have been taking a look in detail at shear failure, and we talked about the unconfined compression strength that was a testing we loaded actually, but actually you get a shear failure if you set up the test correctly. And we talked also about the strength of uncemented sediments, in which by applying a stress in another direction, an effective stress, because of friction, we can hold a higher stress in a perpendicular direction to the one that it's the minimum principal stress. All right, so let's see how we do this in the laboratory and how also this is going to help you to solve the homework, but also it's meaningful to understand why we can have this confining pressure higher than 0. And this is a triaxial test. So for the triaxial test, in the laboratory, we simulate conditions of effective stresses different than 0 in the lab. And in order to do that, we, where's my eraser? We utilize a cell that I'm going to show you in a bit, a simplified version of that. I'm sure I brought my eraser. I cannot find it. Okay, so, oh, here it is. Okay. So, you're going to need a lot of space to do this, okay? I'm going to need an entire page. We get a rock sample. To that rock sample, in order to apply a external stress, effective stress, around the rock, what we use, similar to the coffee package, is a membrane that isolates the rock from an external fluid. In the case of the coffee package, the external fluid was air, but in this test, it's going to be something different. Many times, it's just water, but some other times it's also oil. And these are what we call end caps, made out of usually steel or something a lot stronger than the rock. And we put all of this inside a pressure vessel, which is the one that is going to take a pressure which is going to be higher than atmospheric. So let me finish drawing and I'll show you what those look like. This is also made of steel or strong material. Here in the top, you have a piston or a shaft that goes inside the vessel, and here we put some O-rings, so the pressure inside here and the fluid inside here does not get out. Here we put a load cell. Let's call this load cell number 2, and here we put another load cell, and we call it number 1. Okay, so let me just do one more thing before I show you how those look like. I told you that inside we put fluids that will pressurize the rock and will take it to conditions similar to the subsurface. And in order to do that, here we get a pipe which is connected to a large syringe that applies a pressure. Did you guys ever saw a syringe which weighs about 60 pounds? No? Okay, that's one over there. Next to the low frame, that's that syringe. It's just a syringe, but it moves fluids at a very high pressure. So the fluid gets into, we push it with a syringe, and we push it all inside this confining vessel. So the membrane looks like this. It's not going to be exactly the same that you're going to use in the laboratory, but you see the rock is inside, and around that we have a confining membrane, which in this case is made of a material which is a heat shrink material. So with this membrane now, and with the end caps that go here to the bottom and the top, we can put them inside a container that is going to hold the pressure. This is a container. This is the one that you're going to use in the laboratory. So you see it's hollow. And here you have the connections that go to the pressure pump, but it's just a syringe, high pressure syringe. Probably you can see that, you see here that there is also sort of a shaft that goes, this one moves up and down and just pushes the fluid. And the fluid goes inside here, and we have two ports because sometimes we need to bleed the system so we don't pressurize air. And with that device, we can apply a constant pressure, which is going to be called a confining pressure, and it's going to go with the name of PC. So inside here, we're going to put an assembly that looks more or less like this, where this is another membrane. This is the membrane that you're going to use because it is reusable. But if you were to do this in my laboratory, we use a slightly different system with this other membrane. So it looks something like that. And this goes, again, inside this container, and this lid goes on top, so then it's pressure sealed. So let's see. Let me see if I can get this through. I may need the bench. All right. I think I broke it, but we can replace it later. Okay, so it looks something like this. So by applying a pressure with this syringe and having the fluid around the rock, we're going to be able to apply what we call a confining pressure, and it goes with, it's called PC. Okay? So once we do that, we can vary what is the stress around the rock, and because of the frictional capacity of the rock, the higher that confining pressure, the higher is the stress that is going to resist on the other direction. And on this other direction, we're going to increase the stress with the load frame, and this one, because it is outside this pressure vessel, is the total stress, and it's going to be the total stress S1. All right. So the higher the confining pressure, the higher the stress you're going to need in order to break the rock, because the rock is a frictional material. But let me add one more thing here, which makes the picture complete, and we also need to take into account. And this is the fact that in these kind of tests, many times also we have fluids, and we have a pressure of a fluid. So in addition to this pump, which is the confining fluid pump, we have another pump which is going to control what is the pore pressure inside the rock. And this is going to be an additional conduit that goes connected to the pore system of the rock, and it goes connected to an additional pump. And this is going to be here your fluid pressure. Can be anything, can be, well, could be water, could be oil, could be gas, whatever the fluid you have in your actual rock. And inside here, then you're going to have a pore pressure PP. So then there are three things that we can vary. We can vary the confining pressure, we can vary the pore pressure inside the rock, and by applying an axial load, we can vary the stress and find out what is the stress at which the rock breaks. Okay, this is how you do in the laboratory. And in order to interpret this test, you need to know now how to understand and how to interpret all these variables in the context of effective stress. So always this stress in this direction is going to be higher than the confining pressure. Question, what is, let's say that PC is different than 0, PP is different than 0, and this one is different than 0. For this rock, what is going to be your minimum effective stress using those variables over there? Which one? PC minus PP. Very well. Notice that PC, it's a sort of a total stress, and PP is a pore pressure. So in order to get an effective stress, you need to subtract always the pore pressure. Okay, that's the easy part of the problem. And what is going to be the maximum principal stress? The maximum effective principal stress, we don't have it in the picture, but you know, here on the top we have S1. So it's going to be S1 minus pore pressure. And directly, if you don't have any pore pressure, then your minimum effective stress is PC, and your maximum is directly the axial stress, which in this case is S1. But when you do have pore pressure, then you have to subtract those. Okay, let me tell you one more thing about this and why I put two load cells here. Sometimes it depends on the device that you have, but here, in order to measure this S1, sometimes you measure S1, which is going to be equal to the force divided by area, and that's when you can measure force directly, and that will be with load cell number 1. So here, if I apply a force, and I know the force and I know the area, I know what the value of S1 is. So if you wonder, you know, what does this guy mean with load cell? Okay, this is a load cell. You see this thing that looks like an S. Inside you have strain gauges that measure strain, and according to how much small resistances change length, you get a measurement of force. So this is a load cell, and it is outside. When you do your triaxial cells in the laboratory, you will measure this force, and you will measure directly S1. However, for the homework, it's going to be slightly different, because I'm giving you data from my laboratory in which we have a load cell inside the vessel. And in that case, the load cell inside the vessel already feels the confining pressure, and because it already feels the confining pressure, it's not going to read the value of S1, but it's going to read the value of S1 minus the confining pressure, or S3. And this is what is called a deviatoric stress. And a deviatoric stress, notice that because these are both total stresses, is also equal to sigma 1 minus sigma 3. So if you wanted to compute what is the value of sigma 1, then what you have to do is you have to add sigma 3 to the deviatoric stress, and that's how you get it. So okay, let me finish this. What I just said, this one, usually we call it sigma D for deviatoric, and if you want sigma 1, you get sigma 3, which you know what it is with the confining pressure. You add sigma D, and then you get sigma 1. And if you use the load cell number 1, then just do calculate S1, subtract pore pressure, and that's it. Okay. One more thing very important to notice here is that, remember that for all of these tests, when we refer that at failure, it means what is the maximum value of sigma 1, or the peak value. All right, let's see how this applies to homework number 1. Problem number 1 of shear failure homework.
Quick question.
Yeah.
Does sigma 2 equal sigma 3?
Yes, because in this case, we have an axis symmetric system, and because of the symmetry, sigma 2 is equal to sigma 3. In some other tests, which are more advanced, you can use a cube instead of a cylinder and apply stresses which are different in all 3 directions. That's what is called a polyaxial test. And I'm planning to build one of those here. I'm still working on that. So let me see. I wanted to go here. Okay. So for the first problem, we have an uncemented sand. And in that uncemented sand, if I remember correctly, this is number 5. We have pore pressure equal to 0, and we have deviatoric stress. And this is the maximum value at failure, okay? So in this case, in all these tests, the stress, the maximum stress, was measured inside the vessel. So you don't have the total value of S1, you have the difference between S1 and S3. All right. So my question is, for this particular example, what is going to be sigma 3? So you have PC, you have PP, and you have S1 minus S3. Sigma 3 is going to be directly PC, right? Because this is, the pore pressure is going to be 0. So sigma 3 is going to be equivalent to the minimum principal stress. And sigma 1, the maximum value, is just going to be, as we saw before, the deviatoric stress plus sigma 3. And this is the same. It doesn't matter what the value of pore pressure is, because it's a difference. So the value is still going to hold. So this is just going to be PC plus this value of deviatoric stress, that, let me call it SD. Well, remember that SD is equal to sigma D. All right. So you have sigma 3 and you have sigma 1. We have seen in the theory that these more circles are going to be limited by that shear failure line. Okay, but we're going to go a slightly different route here in order to compute the friction angle, which is a little bit easier. Instead of working in a space of normal effective stress and shear stress, what we're going to do is you're going to plot on the x-axis the minimum effective stress, and on the y-axis the maximum effective stress at failure, or the peak stress. Do you remember, for a typical friction angle of 30 degrees and an uncemented material, what was the maximum stress that you can apply on one direction, given that your confining stress is some value, or what we call stress anisotropy? I told you what's the number you have to remember. 3 times, right? So if I had, let's say, this effective stress, and the material will likely resist value, let me start here, somewhere over there, and that's going to be a point. Each of those rows here, it's one experiment. So there are 3 different experiments. So the first one, let's say PC 3.4, is going to give you, when you compute sigma 1, a value somewhere over here. You go to the next one, which is almost double that pressure, and it's going to be some other value over here. And when you go to the next one, probably it will be some other point over there. These are rocks, and rocks always are heterogeneous. You're not going to get a perfect line. There's going to be some variability, which is natural variability of the rock, and also the natural variability that you may expect in a laboratory test. So, but they will line up. They may not line up perfectly, but they will line up. With that line, and considering that for this one, this is an uncemented material, I like that you fit a line that goes to the, almost through those 3 points. You do basically a linear regression, and hopefully the intercept is going to be close to 0. It should be close to 0. Sometimes it may not be exactly 0, but it's going to be close to 0. I like your jersey of the Braves. I studied in Atlanta. What?
We're going to win today.
Yeah? Against?
Yes.
Who are we playing?
It's the playoffs. We're playing the Cardinals.
Okay, we'll see. Hopefully we win. All right, so I got thrown off by that, but extra points. No, I'm kidding. All right, so what do we do with this? We fit a linear regression, and from here, you're going to get the slope of this curve that we're going to call Q, and the slope of that curve is going to be the maximum stress anisotropy 1 plus sine of phi divided 1 minus sine of phi, where phi is the friction angle. But this is exactly the same as the Moore circle. Is the same line, is the same data. If I were to take this into the Moore circle diagrams, it would be, let's call this one A, B, and C, and where now this is the friction line, this is the friction angle, this is the normal stress, this is the shear stress, this is going to be circle number A, the first test, then circle number B, let me change it slightly. Because your points do not exactly match the line, you should not expect the circles to be perfectly tangent to that line either. So apparently in this case, this one is a little bit stronger than what the shear line predicts. So the Moore circle is going to go a little bit over that. And for the other one, apparently is falling a little bit shorter. So the Moore circle, it might be something like this. But it's just a lot simpler to calculate the friction angle from here than from here. Because if you do it from this type of plot, you have to draw the Moore circles, and then you have to throw a line. I mean, if you do it manually, it's easier. Like you just draw a line eyeballing that more or less goes closer to all of those three circles. But mathematically, it gets a lot more complex. So it's much better to do it in this space than in that space. But then what I want you to do in the homework is to redraw these Moore circles just to make sure that you computed your friction angle correctly. And you should get a line that approaches the circles very nicely. And after you do that, you're going to be able to measure what is the friction angle of this material. Okay. Any question about this problem? No? All right, let's go then to the next one. In the next problem, I'm giving you a test which was done in my laboratory. The first one was done there too. But here, I'm talking especially about the exam. I like that you particularly solved the first problem and the second problem. But the second problem also, it might be a little bit of training for you to computing Young modulus, which is something that you should definitely know for the exam. So this is a triaxial test, and on triaxial conditions, still we can measure strains and stresses. So for this confined triaxial test, what is done is if this is time, what you're going to see is that I don't remember exactly where the data starts, but I'm going to tell you how the experiment is done. The first thing that we do is, and this is what you're going to do in the laboratory as well, we get the sample inside the vessel, but the confining pressure is 0. So before applying any axial stress, what you have to do is you start the test, and then you increase your confining pressure. After you increase your confining pressure, then you increase your deviatoric stress. So this one is going to be 0. Only after you increase the confining pressure, you start increasing your deviatoric stress until this one reaches a maximum and fails. So what does that look in the lab? Well, let me do one more thing over here. Similarly to the test that we did in the laboratory for unconfined compression strength, when you do this, probably let me do it here, it's going to be better. During this time, we do something which is called a constant strain rate experiment. So your strain, your strain is going to be constant at a constant rate, so constant velocity. That means that you're lowering or you're straining the rock at a constant velocity. And that's why you reach a maximum. All the time the rock is shortening, but then at some point it goes over a maximum, and that's when it fails. And what you're going to see from the data is that from here, you're going to be able to calculate Young moduli and the maximum stress, and it's going to look something like this. I'm going to plot here the value of the deviatoric stress. This is going to start at 0, and the more compression you apply, the more the rock is going to deform in axial direction. So this is going to look like this. If you have an unloading cycle, it's going to go down, and then it's going to continue. But then it will go through a peak, and that's the value of sigma d at failure, which is the one that you have to use in these tests over here. Is the maximum value. That's when we're interested in failure. Remember, it's not any of these values, it's the maximum. As you apply that stress, what's going to happen in the perpendicular direction? So we have this rock sample that we're loading it under confining. If the confining pressure is constant, what will happen to the rock? It should expand in the perpendicular direction, and that's going to be the radial strain. And the radial strain is going to look, we have unloading, reloading over there. It's going to look something like this. And this is going to be the radial strain. Let me write it here again. All as a function of the deviatoric stress. And there is one more thing that I want you to calculate, which is something which is called the volumetric strain, and we talked a little bit about that. And The volumetric strength tells you if the rock is actually getting smaller or bigger. When you start compressing a rock in this kind of test, the rock always gets smaller. But at some point, we'll start to change trends and we'll start to get bigger. And at that point, we'll start to dilate. It might not get to the original size, but there's going to be a point in which you will see a change of the trend. And this is the point which is called the point of dilatancy, and many times tells you that the rock is already failing before reaching the peak. That's why usually the Young modulus is measured at a 50% or less of the peak stress, because if it's close to the peak stress, the rock is already broken. When you are analyzing some target formation and you send this test to the laboratory and you get the results back, you should check the stress strain curves and make sure that they actually report Young moduli which are not close to failure, because otherwise those Young moduli are going to be quite different to the ones that you actually need. So again, this is going to be the volumetric strain, and it's going to be an indicator of where the rock starts to fail. And this is basically almost everything I want you to do for that problem number 2. Yes?
How do you calculate volumetric strain?
Volumetric strain for a triaxial test in general is epsilon 1 plus epsilon 2 plus epsilon 3, and for a triaxial test is going to be the axial strain plus 2 times the radial strain because of symmetry. Okay, and the last thing I want you to do in this particular test, or in this particular problem, is after you process all the data, after you tell me what the Young modulus is under confining pressure. Oh, that's another thing that I forgot to say. Usually we do these tests in a triaxial test under confined conditions, because the Young modulus is not going to be the same under confinement that without confinement. Without confinement, usually the rocks tend to be a lot softer than what they actually are when they are confined. So after you compute all of that, I think the last thing I'm asking you for this particular problem is that if, again, now you plot sigma 3 and sigma 1, and if you know at the given value of sigma 3 what is the value of sigma 1 at failure, and if you know something I'm giving you, what is this slope Q, the question is what is UCS? But this is just a line. You have a point, you have the slope. You should be able to tell me what is the intercept in the y-axis, which is going to give you the unconfined compression strain. And this is the last thing that we need to talk about in triaxial failure for now. We talked about uncemented media. In uncemented media, you don't have any confining stress, you don't have any strength at all. But in cemented rocks, even in unconfined conditions, you do have some strength, and that's why we can measure a UCS. So you know all of those very well. This is confined but uncemented. This is a UCS test in unconfined conditions. When you add confinement to a cemented rock, what you get is something like this, with the more circles and this line that it doesn't have an intercept at 0 anymore, but it has an intercept different than 0 that we call cohesive strength. And if we look at that into this space of sigma 1 and sigma 3, now what you get, it's a different value. It doesn't go through 0, but it goes to a value which is UCS. Notice that in unconfined conditions, sigma 3 is equal to 0. So directly, the maximum sigma 1 is the unconfined compression strength. And this equation is going to be the same as that one. And you can go back and forward to either system, and either with Q or UCS or friction angle and this variable which is called cohesive strength with these equations that you don't need to memorize, you don't need to know how to write them, but you need to know that these two things are the same. It's just a different way of plotting the results. And that the further you are from the center or the origin, the stronger your rock is. And something that I'm now plotting here too is that the steeper the line, also the stronger the rock is going to be. That means that it has a bigger frictional resistance. Bigger friction coefficient, bigger frictional resistance, and stronger rock. And just for you to have an idea about typical values of strength of rock, here you can see the UCS of different types of rocks. Usually sedimentary rocks here in brown have lower values than igneous rocks. And carbonates, it depends. Some carbonates are very tough, very strong. Some others not that much. And if we have a uncemented sand, it will go straight to 0. And the bigger the slope, also the bigger the friction coefficient. You may see also more or less that there are some igneous rocks like granite that they have a bigger friction coefficient than usually sedimentary rocks have. We have already seen this, which is adding pore pressure. So the last problem in the homework is about adding pore pressure, calculating effective stresses. And even if your pore pressure is a lot different, but PC minus PP is the same, or S3 minus PP is the same, your maximum deviatoric stress should be about the same. Rocks usually do not depend a lot on the value of pore pressure per se, is on the effective stress or effective confining stress, S3 minus pore pressure. In order to close this topic, let me tell you that this is very important, because what you see over here is that the bigger the pore pressure, the lower the strength of the rock, right? S3, what would be S3 in the context of the field? Minimum total stress. We have seen that many times as a horizontal stress, something that we do not control, something which is there already. But pore pressure we do control. So by injecting fluids, for example in hydraulic fracturing, we can increase pore pressure enough so that the rock becomes weaker by increasing the pore pressure. And by increasing the pore pressure, we can help the rock to fail in shear quite a bit just by increasing that pore pressure, because we are decreasing the frictional strength by relieving that stress in the other direction. So sometimes we could just fail rocks by increasing the pore pressure. Okay, so guys, do you have any question about the exam? Yes?
Does it cover last week's lectures?
It covers last week's lectures. It covers today's lecture, but probably not as much in detail as to solve all the problems for the homework. I do recommend that you solve all the problems for the homework, but for sure, you know, some until UCS, that you should know very well. Okay? Yes? I have, no, you cannot have any sheet to help you But I provide the formulas, I provide the units, so. I can do that. I can do that, but I can tell you, it might not be exactly the same. But if there is anything that you need, I'll tell you during the exam. But I'll upload that. But you already have it in the exam, right? It's the same sheet that you have in the exams I already posted. All right, guys. See you on Wednesday. Please be here on time.